Okay, so you all remember the evolutionary solver model, and let's just go through it again. So we produce in the autumn, winter, and spring. We have a certain level of demand in all three of these periods, and we basically it costs us less to produce in the autumn than the winter, and the spring somewhere in between. So why don't we produce everything in autumn? Well, there is a holding cost. If we have excess inventory that we carry from period to period, it costs a certain amount a unit. And we have to satisfy the demand. We have a series of constraints where basically the net production, what we must, the net production, which is equal to the demand, is basically the difference between the production and the inventory. So say here we produce 550 and 400 goes to the inventory and 100 goes to satisfy demand. And in the next period, we have the same. We've got to satisfy this demand of 400. So 400 plus our net inventory is the production in this period, plus whatever we have over from the previous period. So here, we don't produce anything. We have 400 left over. We don't keep any inventory. So that matches the 400 for demand. And then the similar thing happens in the spring. Here we actually produce the remaining 50, and this 50 goes towards the demand. And you can see here what's happened is that the winter, it's very expensive to produce. It's actually cheaper to produce in the autumn and hold over. So all the demand for the winter is also produced in the autumn. But actually going ahead 2 periods, $11 plus holding for 2 periods would make it 11.20, 12.40. Sorry, 12.20, 13.40, which is actually more expensive than producing in the spring. So we produce the 50 in the spring. Now, very simple kind of linear programming. But let's just say we also have these fixed costs. And if we produce in any one of these periods, then we incur a fixed charge of $65. Now, the whole idea of what we're doing here, we're going to use the evolutionary solver because the standard linear program and nonlinear program is not really easily tractable when we have these kind of more complex objective functions, things where we have absolute values or maximum values. Now, there are ways of maybe modeling these in a slightly more sophisticated fashion, but if we want something easily understandable to our clients, we might just say, okay, if our production is greater than 0, we have this charge of 65 um, for kind of each of these periods of production. So let's just add that in. Plus if okay, so if this production, if we produce in this period is greater than 0, then we incur this fixed cost. Otherwise, we incur 0 plus, we can do the same for C, and we can do the same for D, the spring. So there we go. We have the sum product plus if B13 is greater than 0, we have B9, otherwise we have a 0. If C13 is greater than 0, so if production in the winter is greater than 0, then it's going to be 65, otherwise it's going to be 0, and so on. And again, this is very difficult to actually do as a linear program. So let's try and solve this in Solver. Okay, so let's set the objective here, which is to minimize the cost by changing these variables, subject to our previously done balance constraints that our net production, which we send out, is equal to the required demand. And generally, we also have to, for evolutionary solvers, we have to constrain these variables. And we're going to constrain them to be less than or equal to 600. And we do that because the production is never the total demand is 600. So there's never going to be any stage where we would actually want to produce more than 600. It would just be wasted demand. So let's just click that. The book also has greater than 0 constraints, but that's included here. Now, let me just say this doesn't work particularly well. There's several reasons for this. It's kind of quite a complicated algorithm. It's basically a genetic algorithm. What it does is it creates lots of solutions, and then it will kind of slowly mutate, kind of combine solutions, mutate solutions, and then we'll try and eventually get almost evolve good solutions. This is why it's called the evolutionary variable. And let's actually put require bounds on variables, as we've already bounded the variables. And I think that's pretty much it. Let's click solve. Now, this actually takes a couple of minutes. Now, I'm going to do my own version of this, which works, I think, much better. The issue is here. It's kind of hard to calculate these functions. Um, these are also continuous variables, which makes it kind of hard to do evolutionary solver. Um, so this result I'm going to tell you now, because I've checked it a few times before, isn't actually very good, and it doesn't kind of quite meet the constraints. But I'll show you maybe, I just want to do the book method, but I'll also show you a slightly better method in a minute. I'll just pause the video while it runs. Okay, here are the results, and frankly, it's a little bit underwhelming. It's tried to move some of the constraints, but it really hasn't managed to keep the demand and inventory constraints. Okay,